Anyway, all that stuff before, I'm not testing you on. From here, this is fair game. Benzene, C6H6, and they thought, well, maybe it's something like this, where I've got, let's make these triple bonds. C, triple bond, C, CH, double bond, CH. I guess it'd be CH2, CH2. CH2, CH2, triple bond, CH. Even some weird ones like this had been proposed, which is also C6H6, or even a compound that looks like this. The long bond there, what this one would look like this. Would look like a sort of like a little roof. These hydrogens would be sticking out toward you. And this compound actually exists. But none of these really seem to work until Kekulé in 1866 came up with this idea that benzene was this structure. Now, whether he actually came up with this by himself or he stole it from one of his contemporaries, I think of someone named Loschmidt, or he had this drunken hallucination about a snake grabbing its tail. There's evidence for all three. But this is called Kekulé structure for benzene. And the interesting thing about it is, with all these things with double bonds, you'd expect it, we all know that a double bond reacts with hydrogen in the presence of a catalyst to give, in this case, you'd go from ethylene to ethane. We know that a double bond reacts with potassium permanganate to form a diol. We know that those things happen. But benzene doesn't do any of those. It doesn't react with hydrogen unless you're putting it like under 1,000 pounds per square inch of pressure. These things would react immediately, but benzene doesn't. Benzene doesn't react with potassium permanganate. It does a lot of, it's stable to a lot of things that a typical alkene would react. Also, it's known that if you take something like, we'll just say bromine. We know bromine reacts with double bonds to give addition products. Bromine can dissolve in benzene and doesn't react, but if you add a catalyst, iron 3 bromide, you get bromobenzene plus HBr. You get substitution. You do not get addition. So that seems weird. And for compounds like these, where there's hydrogens on the end and hydrogens on the middle, there's two places the bromine could have gone. The bromine could have gone here, or various places on there. There's a number of compounds that were proposed, but only one C6H5Br, only one bromobenzene has ever been isolated, which makes this structure make sense. And if I repeat the process using iron 3 bromide, Br2, FeBr3, I get 3 isomers of C6H4Br2. And that would make sense if I have let's call this the number 1 position. I could have the 1,2 isomer, the 1,3 isomer, and the 1,4 isomer. So that would make sense, 3 isomers. But let's pay attention to the 1,2 isomer real quick, because Kekule, if you draw it out with the double bonds, I could draw it like this, or I could draw it like that. Here, the substituted carbons have a double bond in between them, and here the substituted carbons have a single bond in between them. It looks like they're different compounds. And Kekule proposed that there was a rapid equilibrium between the two. But if you take this stuff and freeze it, make a crystal, and then bounce X-rays off the crystal, the scattering pattern depends on the location of the atoms. And it's been determined that this is a perfect hexagon. That all of these bonds, we know that a double bond is supposed to be shorter than a single bond. And so you'd expect the CC bond distance between these two carbons, that the bromines be closer together or further away and switching back and forth, but it's not, it's a hexagon. All the bonds are the same length, which is why sometimes we draw a circle to show all the bonds are equivalent, and that these 6 electrons in the ring are delocalized. They're not fixed to the same position. And so let me just talk really quickly about, I've already mentioned about the stability of benzene that in section 16.2, that while double bonds react with potassium permanganate, that they react with bromine by addition, that they react by hydrogenation easily. Benzene doesn't do any of those. But let's look at an energy diagram here for some comparison. And this is the diagram reproduced, figure 16.2 on page 767. And I'm not going to put in the exact numbers, but if we have this level here as the energy of cyclohexane, cyclohexene, if I hydrogenate it, I get out about 20, well, I don't know why they put it in those terms. It's about 28 kilocalories per mole. Now there's 2 cyclohexadienes. One is the non-conjugated one, and one is the conjugated one. And here I get out, is like 28.6, and I get about 57.4, which is almost exactly twice the energy of a single bond, because those double bonds are isolated. Here I only get out around 55.6. So there's a little bit of stabilization here because those bonds are conjugated. But now let's think about benzene. If benzene existed as a 3 pi bonds, that if it really existed as, I'm going to have to draw this up here because I'm out of scale, that if it really existed like that, it would be about here, which would be about roughly 85.6 kilocalories per mole. But it's not. Instead, if you hydrogenate benzene, you only get out about, you don't get this, you get about 49.6 kcals per mole. Benzene is actually more stable than the dienes. And so I'm used to putting the because the electron delocalization here, it's very, very stable. And this 36 kilocalorie difference here, is known as resonance energy, which I think is kind of a bad term. It's 36 kilocalories per mole of resonance stabilization is a better term. It also explains why things like this don't happen, because if the double bonds were fixed and I added bromine and I got and I break the aromatic ring, you'll notice I'm going from here up to here. I'm going uphill instead if I break the ring aromaticity. That's why it doesn't like reacting by addition. You can make it add by addition, but it takes some special circumstances. It's why you don't hydrogenate benzene easily, because you'll be going uphill. So, the idea that, okay, any questions about this before I explain where this idea kind of starts to fall apart about resonance is good? Because we're going to come up to remember I said there was an exception about resonance stabilization? We're there. Okay. Well, we know that benzene, I showed the different resonance structures. And it's sort of like the idea behind the Diels-Alder reaction. If we can take a 4 and a 2 and make a 6, then we can take a 2 and a 2 and make a 4. Doesn't work. We can take a 4 and a 4 and make an 8. Doesn't work. So they thought, well, how about if we can take cyclobutadiene, I'm going to CBD, cyclobutadiene. And these compounds are called the annulenes. I'll write it here. ANNULENES. Annulenes. And this one, because it is a 4-membered ring, would be called 4-annulene. But this stuff has never been isolated. It can be generated, but it immediately reacts with just about anything it touches. And you can take a precursor to this, and I'll just show you the reaction here real quick. If I take this compound, which has an ester group in it, and I freeze this in argon. Now, argon makes up 1% of our atmosphere, and it's completely inert. I can freeze this in argon atoms. I'm going to use those circles to represent those. And I hit this with light. and I get CO2. But see, this is still surrounded by argon, so it can't react with anything. Remember, this argon is frozen in place. And you can actually take an IR spectrum of this, and it's not a square. It's a rectangle. The double bonded ends are slightly shorter. It's not a square. So you might think, oh, well, is that this, there's no equilibrium here between these, and there's no resonance between these. And so cyclobutadiene is what is called anti-aromatic. If aromatic, like benzene and some other compounds, represents something that's more stable than you would expect, anti-aromatic means it is less stable than you would expect, and cyclobutadiene certainly qualifies. Yes, there's angle strain because these angles are necessarily 90 degrees. But that's not enough to explain why it is impossible to form. You should be able to see it at least for a few moments, but you can't. Now, benzene itself, we know. You could also call that 6-annuline. Very stable. This is aromatic. I'm going to write AA. AA for anti-aromatic. AR for aromatic. So that's, we have a 4-membered ring, a 6-membered ring. What's next? 8. Cyclooctatetraene, which I abbreviate COT. Cyclooctatetraene. And this stuff is weird. This is highly reactive. This doesn't react very much, but this reacts like a typical alkene. COT, you can hydrogenate COT, you can add bromine to the COT, you can add permanganate to the COT, and it reacts just like an alkene. It turns out that this molecule actually exists as a tub-shaped molecule, where the p orbital's here and the p orbital's here, and these ones are over here in this way, and these ones are sticking their own direction. That the p orbital, it's not flat. It's not a flat molecule. And this is, sometimes I'm just going to write Na for non-aromatic. In other words, it behaves like a typical alkene. There's nothing especially stable about it. There's nothing especially unstable about it. That's non-aromatic. So that's 4, 6, 8. Let's look at 10. Now you can write the 10-membered ring in a couple of different ways. One of them, the bond angles here are 150 degrees, and so this has too much angle strain. It really doesn't like being in that shape. But you can write it like this. Now that looks perfectly reasonable, 60-degree angles and everything. The problem is these hydrogens here on these carbons will be bumping into each other's space. And so I'm going to use these markers to represent the p orbitals on those carbons, and my thumbs will represent the hydrogens. They're in each other's way, so they have to tip a little bit to make room. And I should have worn a lighter shirt. But you notice now the p orbitals are slanted. All the other p orbitals are straight up and down, but these guys are slanted, so it's non-aromatic. You get to 12, so 10-annuline, is non-aromatic. 12-annuline is non-aromatic. 14-annuline is aromatic, but not nearly as stable as benzene. But it is more stable than you would have expected. 16, not aromatic. 18-annuline is aromatic. And this pattern goes on. But once you get up to about to about 30-annuline, it just kind of, the effect diminishes as you go. The larger the molecule, the less the effect. And once you get to about 30, it all just behaves like alkenes. So what rhyme or reason is there to this? This doesn't make a whole lot of sense. Well, to understand this and make a little more sense of it, let's look at the structure of the orbitals of benzene. And then we'll see why this pattern is the way it is. Why cyclobutadiene is anti-aromatic, why COT is non-aromatic, and so forth. And this is given on page 770. Benzene, we know, how many p orbitals in benzene? 6. So if I've got 6 p orbitals here, how many molecular orbitals can I make? Give you 2 sips of coffee before I give you the answer.
6.
6 it is, because if I take X number of atomic orbitals, I get X number of molecular orbitals. Some of them may be bonding, some of them may be anti-bonding, some may be non-bonding, but it's always I get the same number. And a way to illustrate the energies of these orbitals is to use a hexagon. This thing is sometimes called a Frost's circle. And the way to do it is to simply draw a circle and then inscribe your polygon, point down, and then bisect it. This is your non-bonding line. Any orbitals below this line are bonding, any orbitals above it, anti-bonding. Well, and where it intersects, I'll put it in red to make it stand out a little better. Where the line touches the circle, that's the energy levels of your orbitals. And so we have psi 1, and then psi 2 and psi 3 are the same energy. Psi 4 and psi 5 are the same energy, and then psi 6. Now, how many electrons am I dealing with here? In benzene, anytime you got pi bonds, how many electrons is that? 2, 4, 6. So 1, 2, 3. I had to go over here for 4. Remember Hund's rule with when you're filling up orbitals? Remember nitrogen? It's 1 for you, 1 for you, 1 for you. Then I go back and fill up with seconds. Got to fill them evenly. So psi 1, 2, 3, 4, 5. I'm going to make that a little heavy so you can see it clearer. And then 6. All 6 electrons are in bonding orbitals. And if you look at the diagram on the top of page 770, figure 16.4, you'll see that psi 1 has the electron density over the entire thing, which isn't that what we talk about with benzene, that the electrons are delocalized, that they're spread over the entire ring? Well, that shows you right there. So it makes sense that benzene is going to be especially stable. But what about cyclobutadiene? What about CBD? Why is it weird? Well, let's make a frost circle for that. Here's our circle. We'll inscribe a diamond. Remember, point downward, bisect it. Okay, I can't necessarily draw a straight line when the board moves, but anyway, you get the idea. And how many electrons for cyclobutadiene? 4. So let's fill them in. 1, 2, 3, 4. And we've run out of electrons, haven't we? Houston, we have a problem. We have a molecule which has 2 unpaired electrons in it. Well, 2 electrons make up a bond. So since and remember, they had to be paired to make a bond. So since I have 2 unpaired electrons, this is essentially loss of 1 bond's worth of stabilization. And since a carbon-carbon bond is like 60 or 70 kilocalories per mole, that's a lot of destabilization you've got there. Losing a bond is, that's losing a huge amount of chance to become more stable. And so if cyclobutadiene was delocalized, if it was a square where all the electrons were spread out, it would have to exist in this shape, which throws away a bond's worth of energy. It exists instead in the rectangle shape, not going back and forth between these. It's a rectangle, not a square, because if it's a square, it becomes even less stable. Cyclobutadiene is, like I said, this is anti-aromatic. And this is a case where, yeah, I could theoretically draw resonance structures for cyclobutadiene, but it doesn't help. Because you're assuming the for resonance structures, it has to be a square. For a square, you're losing energy. You're not getting all the energy out that you could. So for an aromatic system, the delocalization makes it more stable. For an anti-aromatic system, delocalization of the electrons makes it less stable. And as we'll see when we talk about trying to figure out, is it aromatic or anti-aromatic or non-aromatic, the rules for aromaticity and anti-aromaticity are almost the same. Almost the same. Now, let's look at cyclooctatetraene, COT. We'll see how good I am at drawing octagons. It'll work. And you'll note, by the way, you'll notice that these electrons in cyclobutadiene are on the non-bonding level. So they neither make it more stable or less stable. We want orbitals to be below the line. So cyclooctatetraene, how many electrons? Got 8. 1, 2, 3, 4, 5, 6, and you know what's coming next, 7, 8. So if cyclooctatetraene was an octagon and planar, then it would be less stable. And the part about planar, it has to be planar for the p orbitals to line up. And so that is why cyclooctatetraene exists in the tub. Because the molecule now has, because you have more carbons in there, you have more flexibility. You can't flex out of a, if you have 4 carbons there, you can't flex. But when you have 8, there's enough room you can flex, and now the p orbitals don't line up with each other. In fact, this ring, the tub can turn inside out. And the energy of the, and it's supposed to go through a anti-aromatic transition state, and they've calculated it matches. That's why it doesn't like flipping. You have to really heat it up to get it to flip. So 10-annuline we talked about with the orbitals, with the hydrogens being twisted. 12-annuline, you can see the pattern here. 4 is anti-aromatic. 6 is aromatic. 8 is anti-aromatic. 10 would be aromatic. The downside is it can't because the hydrogens get in the way. But what about 12? 12 would be aromatic or anti-aromatic if it's flat.
On the last bit, we said that tin was not aromatic.
Right. It would be if we didn't have those hydrogens banging into each other.
Okay.
If it wasn't for these hydrogens here, 10 would be aromatic.
Okay.
But that, that's a problem. So 12 would be what? Anti-aromatic. 14 we already said is aromatic. 16 would be anti-aromatic. 18 is aromatic, and so forth. The thing is, once you get to C 8, 12, 16, 20, those are flexible enough that they are non-planar. And if they're non-planar, they're non-aromatic. because only planar systems can be aromatic or anti-aromatic. Because aromaticity and anti-aromaticity have to do with delocalizing the electrons. With aromatic systems, delocalization is a good thing. It makes it more stable. Anti-aromatic, delocalization is a bad thing, makes it less stable.
And because, so when you get to 8 and it has that trough conformation, that's where aromatic stops.
Where, no, it's if it can become non-planar, then it will be non-aromatic.
Okay.
If I could lock a 12-membered ring into a planar shape, it would be anti-aromatic. It would be destabilized. A 14-member ring will be planar because it's aromatic. So what do we have here? For aromatic, the number of electrons in the system, 4n plus 2 electrons in p orbitals. Now the n is just a counting number. So if n equals 0, you can have 2 electrons and have an aromatic system. 6, 10, 14, 18, etc. And you see benzene certainly fits that number. For anti-aromatic, it's a 4n system. In other words, a multiple of 4. So if I have 4 electrons in p orbitals, it's anti-aromatic. So 4, 8, 12, 16, etc.
Oh, what's n again?
It's just a counting number.
Okay.
There's no significance to n. Just like if I define an odd number as, you can define an odd number as 2n plus 1. Whatever n is, if you add 1, it becomes an odd number. So there's no significance to n. It's just if I take these numbers, they fit this equation. If I take these numbers, they fit this equation. And non-aromatic is something that doesn't fit one of the other two. I'll give you a more comprehensive definition just now. A system is aromatic if it has a cyclic arrangement or network of overlapping p orbitals and by definition that means it's planar because you can't have a network of overlapping orbitals if it's not planar. Think about the tub of cyclooctatetraene. And it has 4n plus 2 electrons in the network. This is aromaticity. Let me get it. If it's aromatic, a cyclic network of overlapping p orbitals that contains 4n plus 2 electrons in the network. One of these numbers up here. For anti-aromatic, it's exactly the same term for number 1. For anti-aromatic, number 1, same as above. So number 2, 4n electrons. So aromatic and anti-aromatic are very similar in a lot of ways. Non-aromatic is anything that isn't one of these. So it could be an odd number of electrons. It could be non-planar. It could be non-cyclic. It may not have a continuous network of orbitals. So I'll give you some examples of non-aromatic systems. That has 6 electrons in it, but my network is not a circle. It could be like this. It's a circle. It's got 6 electrons, but look at this carbon over here. This carbon is sp3 hybridized. It doesn't have a p orbital. And so this is non-aromatic. And of course, if it's not planar, it's not aromatic. Here's one. Let's just take this. Oops. Try drawing a better pentagon than that. If I have a radical here, that's an odd number of electrons. I have 2 electrons from this pi bond, 2 electrons from here, and 1 there. Yes, I have my overlapping p orbitals in a ring, so it's planar, it's cyclic, it's got the p orbitals all in a ring, but it's got an odd number of electrons, so this is non-aromatic. So it's sort of like just basically aromatic and anti-aromatic are 2 sides of a coin. Non-aromatic means it doesn't fit one of these 2. And this whole thing was developed by a guy named Huckel. He came up with this idea of filling up the orbitals 2, then 2, then 2, and so forth, in the diagrams shown on page 777. But his rule, number 1, it didn't say anything about it had to be a carbon atom, which it doesn't, as we'll see when we look at section 9, and in section 8, which we'll get to on Thursday. It also doesn't have to be neutral. There are ions, hopefully for example, this ion here with a negative charge on that carbon, it has 6 electrons in this system. So it would be aromatic. If it only had a positive charge here. I have a p orbital for that. This would have 4 electrons and would be anti-aromatic. We'll talk more about that in section 8 on Thursday. We'll look at section 8, 9, and a little bit at 10. You can skip the section 11 entirely. And I'm going to leave nomenclature, which is section 13. I'm going to leave it to you to read up on, because the book does nomenclature fairly well. And so there's nothing I can add to section 13 very much. So I'll leave that for you to study on your own. You can skip section 14 and 15, and that takes you out the end of the chapter. So 8, 9, 13, and that'll take us through chapter 16, and we'll start chapter 17. For chapter 17, you should read up through about section 4. We're going to do things a little bit out of order in that chapter, so we'll have to be flexible because they put things in an order I don't like. Check your syllabus for more details. Anyway, that's it for today. I'll be around for office hours today. Tomorrow I've got an appointment at 1 o'clock, so I have to, we'll have to end office hours just a tad early. But anyway, I will send out answer keys for the quiz, and probably put some comments on your papers if I can do so. And I'll see you tomorrow. Have a good day, everyone.